In this supplementary video, we will solve two very tricky problems regarding the application of the intermediate value theorem. So for this problem, suppose f is a continuous function on the closed interval 1 to 5, and the only solution to the equation f of x equals to 6 are x equals to 1 and x equals to 4. Okay, so you are also given the information that f of 2 equals to 8, and you need to prove why f of 3 is greater than 6. All right, so now let's actually see what do we have over here. So what we know is that f of 1 equals to 6 and f of 4 equals to 6. So these are two solutions where f of x equals to 6. And moreover, we are also given the information that f of 2 equals to 8. To prove that f of 3 is strictly greater than 6, all we need to do is to exclude the possibility for f of 3 equals to 6 and f of 3 is strictly smaller than 6. Okay, so the first possibility is quite easy to exclude. So f of 3 equals to 6 is impossible. Otherwise, f of x equals to 6 will have solutions x equals to 1, x equals to 3, and x equals to 4. So contradictory to our assumption. All right, now let's investigate if it's possible for me to have f of 3 to be strictly less than 6. So if f of 3 is strictly less than 6, then since f of 2 is equals to 8, which is strictly greater than 6, and the function is continuous. So originally the function was continuous on 1 to 5, but now 1 to 5 is containing the interval 2 to 3. So in particular, we know that the function is also continuous on the interval 2 to 3. Collecting these facts and apply the intermediate value theorem, we see that there exists a number c sitting between 2 and 3, such that f of c equals to 6. Well, but if f of c equals to 6, then we can conclude that f of x equals to 6 has solutions x equals to 1, x equals to c, x equals to 4. So this is again contradictory to our assumption. Because we assume that the only solution of the equation are x equals to 1 and x equals 4, and x equals to c is not supposed to be a solution. All right, we argue that f of 3 equals to 6 is impossible, and also f of 3 less than 6 is contradictory to our assumption, so therefore it is also impossible. So the only remaining possibility is f of 3 to be strictly greater than 6, and that will conclude our problem. Okay, let's look at number 62. We want to prove that the graph of y equals x squared minus 3 plus 1 over x over this interval. Notice that this is an open interval. We want to show that the graph of this function has at least two x-intercepts in 0 to 2. So this means we will be able to find two numbers, c1 and c2, such that when x equals to c1, when x equals to c2, y is going to be equals to 0. So this is what it means. Okay, so for convenience, let's start by setting f of x as the function we are considering on the right-hand side. And this function is defined over this open interval over here. So notice that we are not given a continuous function on a closed interval, so we cannot directly use the intermediate value theorem. However, the limit at the endpoint will tell us something about this function. So notice that as x approaches 0 from above, x squared minus 3 is approaching 0 minus 3, which is a fixed number minus 3. But the component 1 over x is approaching positive infinity. So 1 over x is very large. while x squared minus 3 is just a fixed number. So this will tell me that my f of x being the sum of a number very close to minus 3 and a very large number. So this will also be a very large number as x gets close to 0. Okay, so we know that f of x has the limit infinity as x approaches 0 from the right. So in particular, so this tells me that f of x is positive as x gets close to 0. For example, we can try x equals to 1/4, then we see that f of 1/4. So this is going to be equals to 1/16 minus 3 plus 1/1/4, and the answer will be 1/16 minus 3 plus 4. So minus 3 plus 4 is a positive number, and together with 1/16 in the front is also going to be a positive number. So then I can conclude that f of 1/4 is positive. Okay, now we could also investigate what happens if x equals to 1. So then we see that f of 1 is simply going to be 1 minus 3 plus 1, and then the answer will be minus 1, which would be smaller than 0. Okay, so we could now apply intermediate value theorem to the continuous function f of x equals to x squared minus 3 plus 1 over x on the closed interval 1/4 and 1 to conclude that there exists C1 sitting between 1/4 and 1 such that f of C1 equals to 0. All right, so that way we find our first x-intercept. Okay, to find another intercept, let's look at the limit as x approaching 2 from the left. So in this case, we see that f of x being x squared minus 3 plus 1 over x is approaching 2 squared minus 3 plus 1 over 2. That will be 4 minus 3 plus 1 over 2. And then we know that this guy is strictly positive. So in particular, this basically says the same, that f of x is positive as x gets close to 2. So for example, we could then try x equals to 7/4. So that we will see that f of 7/4 is going to be equals to 49/16 minus 3 plus 4/7. But notice that 49/16 minus 3, it's simply going to be 49 minus 48/16. The answer will be 1/16. That's positive. Together with the 7/4 afterwards, so we see that this is going to be a positive number. I don't really care the precise number we should get over here. Okay, what happens if 7/4 doesn't work? What happens if you computed some negative number? The answer is just to find another close number that's closer to 2. So if f of 7/4 is negative, so then try another number close to 2. So we managed to find a number where the function value is positive. Then now, together with the fact that function value at the point 1 is negative, so we could use our intermediate value theorem to the continuous function f of x on the interval 1 to 7/4, we conclude that there exists C2 sitting strictly between 1 and 7/4, such that f of C2 equals to 0. So our conclusion is x equals to C1 and x equals to C2 are the two x-intercepts to the graph y equals to f of x. All right, so that concludes the proof of this problem.